Momentum is one of those words that, and actually like quite a lot of words, because we use speed and velocity pretty much interchangeably in everyday life. But in physics, we have to be careful about the difference, because one we care about direction, the other one we don't. Momentum is one of those words that we use in political campaigns. Does this particular candidate have momentum or not? That sense of moving forward, that sense of being in a positive place, being able to do the things that we want to do. So momentum we use metaphorically in everyday life. A project at work might have momentum, or it might be losing momentum. But as a physical concept, it's about the fact that it takes work, it takes a force to start something moving, and it takes a force to stop something moving. So we also talk about inertia, which is that quality of requiring a force to change its movement. And we'll talk about that more in relation to Newton's laws in a little while. But just momentum, quite quickly, I think. We already mentioned that it takes a force to stop something when it's moving, and it takes a force to start something moving when it's not. Remembering that motion is relative, so it depends on our frame of reference. So if you are on a train and you want to start running, it will still take a force to start you moving, although you're already moving relative to the ground because you're not moving relative to the train. So it's about your frame of reference. So we'll talk a bit more about that. To calculate it, to kind of quantify it a little bit, the momentum is given by, momentum P is given by the mass times the velocity of the object. So the mass is in kilograms and the velocity is in meters per second. So the unit of momentum is kilogram meters per second. It doesn't have a neater name than that. It's just kilogram meters per second. So momentum we find is conserved. That is, the amount of momentum that you start a collision or an event or something with will be the same amount that you finish with. So quite often you'll find that if something collides, so we'll talk in a minute about pool balls colliding, because they're a nice, clear, visible example of momentum. If something collides, the momentum can transfer from one thing to another. It's not created or destroyed, but it kind of sometimes seems as though it is. So if you're driving along in your car at 100 and you have a mass of 2,000 kilograms, remember we said 100 kilometers an hour is about 28-ish meters per second. So you have a particular momentum of the car and then you slow down and stop. Well, where did that momentum go? It actually went into the earth because you slowed down by braking against the road. But of course the earth has an immense mass, something on the order of 10 to the 30 kilograms. So it doesn't really change its velocity by any noticeable amount at all. But the momentum's still being conserved. It's just gone into the earth. It's moved particles in the surface of the road and so on. So momentum is conserved. We can't always see it being conserved, but we know that it's conserved. So if we're actually analysing a collision, so I've got my two pool balls. They have the same mass, but we'll call them ball 1 and ball 2. Ball 1 is coming in at 3 meters per second. Ball 2 is stationary. They have mass 1 and mass 2. If you look at the equation on the slide, those should be subscripts. So it should be m lowercase 1 subscript v1 m2 v2. And again, it's actually arbitrary which we choose to be which. I could decide that this is ball 1 and this is ball 2, but for our purposes, ball 2 is stationary. It's not moving, so it's v, velocity, v2 is 0. So that whole term, m2 v2, is 0. There's no momentum in a stationary ball. The moving ball has its mass, whatever the mass of a pool ball is. It's coming in at about 3. And what we usually see is it comes in, collides with the stationary ball, and the stationary ball moves off at about 3. So the momentum has been transferred from this one to this one. We've got the two balls transferring momentum from one to the other, and it's been conserved overall. We can actually calculate the velocities of the balls before and after by using the fact that their momentums are, the overall momentum of the system is conserved. We're going to talk a bit more about energy in week 6, but kinetic energy, the energy of the motion, is not always conserved because some of it's lost. You imagine the pool balls coming together and clicking. That noise, creating that noise, requires some energy. So the second ball will move off with slightly less speed than it otherwise would have because some of the energy hasn't been transferred, it's been wasted, sent off as noise, maybe some as heat, some as in other ways. So we'll talk about energy more later, but for now, for momentum being conserved, having the notion of P equals mv, and having that notion of how do we actually calculate the momentum before a collision and then the momentum after a collision, and use that to calculate other things that we're interested in. And we'll give you some examples of those to do.